Great to be here. Kudos to the organizers. My wife asked me, why are you going to this meeting? And I said, because these are my people. I can't imagine being in a room with more people that are, I think, really interested in the general area that we've been interested in for quite some time, which is this issue of how do you program matter from the bottom up? How do you begin to build colloidal crystals where you build structures on demand and have a target in mind and have the ability to put together the right types of building blocks to generate them in a deliberate fashion and then ultimately design architectures that have properties that you want by controlling that type of structure. This is a work that's been going on now for about, 3 decades. It started back in '96, as Sharon said, and has come really quite a long way, in large part because of contributions from many people. There's lots of grad students and postdocs along the way, but also many collaborators. I've listed some of them below here. Corey Aden on the optical side of things, along with George Schatz. Sharon Glotzer, who you've heard from already, George and Monica have been huge in terms of the simulations and understanding, helping us understand the dynamics of what's occurring, assigning structure. As you'll see, a lot of the structures are quite complicated, and it requires an interplay between experimentalists and theoreticians to really do that accurately. Byung-Du Lee, who is involved in a lot of our work and very important in terms of the small angle X-ray scattering work done at the synchrotron. And then Vinayak Dravid, who plays a big role in a lot of the electron microscopy. You might ask then, what the heck do I do? We actually spent a lot of time on the chemistry side of things thinking about how we create design rules using oligonucleotides and particle building blocks to, as I said, ultimately control the types of assemblies that you're going to see. Everything I'm going to talk about really starts with, I like to say, one tiny particle. The first particle is actually a gold particle, heavily modified with oligonucleotides. We now refer to it as a spherical nucleic acid. That's primarily descriptive, but it's really an important type of observation because those types of constructs really represent a unique form of nucleic acid in their own right. They also represent this concept of a programmable atom equivalent. And I like to put this up here because I think sometimes we get caught up in, as we heard in the discussion earlier, what are these good for? What can we ultimately use these types of materials for? We did not set out to do any of this to develop things that were technologically important. But it turns out the particle building blocks themselves are really quite important already. And they're used heavily in the area of molecular diagnostics and commercialized systems. The Verigene system, for example, which was commercialized by Nanosphere, a company we started, bought by Luminex, then bought by Diasorin. It's everywhere. It's all over the world, used for point-of-care medical care. And the particles are actually used as labels in those types of diagnostic tools. They're also parts of clinical trials. There are drugs, the basis for drugs that are used for gene regulation, antisense, siRNA, and also vaccine development. So when I talk about a lot of what I'm going to refer to in terms of colloidal crystal engineering, this is the basic building block. And we were not setting out to do that, but that's what ultimately came out of that. And I think the same will occur with a lot of the types of materials, these extended materials that I'm talking about as well. So I think it's important for us to keep our eyes on what we can do with these types of materials, but it's also important to realize that fundamental research ultimately leads to discoveries, that leads to new technologies. And that's been true of the basic building blocks, and I think it's going to be true of the types of materials I'm going to share with you today. And so the way we got into this was we were thinking about how we could take particles and effectively create programmable atoms. And I was watching a lot of people talk about particles as building blocks to build colloidal crystals, and they were using electrostatic interactions, they were using short molecules that would link particles together in certain cases. And I realized that if we think about these as atoms, they were kind of working on the wrong scale, at least from my perspective. If we amplify the size of the atom up to the nanometer length scale, we have to amplify the length of the bond to keep the metaphor consistent. If we simply use conventional cross-linkers in the case of organic chemistry, or even polymers, simple polymers, we run out of interaction pairs very, very quickly. And so then I immediately thought about this and said, the best type of polymer in this particular case would be an oligonucleotide or a peptide. And so those became the two kind of targets in terms of how we thought about building these types of architectures. Create rigid rods, and you could program recognition properties. A 17 base long oligonucleotide can have 4 to the 17th different combinations. Not all of them are orthogonal in terms of interactions, but a lot of them are. And so that gave us then the right length scale and the ultimate ability to build programmability in a way that we couldn't realize with other types of materials. That was kind of the origin of all this. The general goal was to try to effectively compete with nature. Learn how to build colloidal crystals where we could dial in structure and dial in properties and hopefully go beyond natural systems. You guys know all this, I'm not going to go through this, but the parameters we were interested in were crystal symmetry, lattice parameter, bond length in the vernacular I'm going to refer to, composition, crystal habit, and also reconfigurability. I think one of the interesting things about using oligonucleotides as bonding elements is that it's a molecule. It's not electrons. It's not fixed. I can create it in many different forms, and I can create a type of reconfigurability that I can't get with electron-based interactions. And so from a chemistry standpoint, the way we think about this is chemists work with atoms, use electron-based bonds, make molecules, zip molecules together to make materials. We're effectively trying to turn particles into programmable atoms, modifying them with the appropriate oligonucleotides, defining the rules then to assemble them into colloidal crystals that have properties based upon where we put each of those basic building blocks within the extended structure. And so I want to share with you some of the recent advances. I have to take you a little bit through the history to get you up to speed, but I want to talk a lot about some unpublished work that we have that I think is going to address some of the questions that were brought up throughout some of the earlier talks. And I want to focus primarily on both structure and properties. We got into that little discussion about the importance of I'm a big believer, so don't get me wrong. I was coming out aggressively, but because I want to protect this idea of controlling architecture. Everything starts with architectural control, and I don't think we should ever apologize for that. Expanding what's possible in terms of controlling structure is a worthwhile pursuit in its own right. It's also reasonable to ask, how do I actually use those capabilities to dial in properties that I want? They can either mimic what we find in nature or exceed what we find in nature. So this is the mess Sharon was talking about. It's like criticizing a baby. I mean, I look at my children, and that was beautiful to us back in the 90s, right? You take particles, and this was a big deal back then, interfacing two very different materials, oligonucleotides, structures that you could make in the course of an afternoon, modify on one end that will allow you to anchor to a particular particle. In this case, modifying gold particles, where you could create two batches of particles that could recognize one another, mix them together, and it was pretty amazing because these would come together, they would assemble into aggregate structures. There'd be a plasmonic shift, which was the basis for why we moved down the development of biological sensors, because there was a colorimetric signature that was amplifying the recognition event that led to that aggregation, right? This was the first step to crystallization, though. We actually had the dream of trying to utilize these types of particles to build architectures on demand. There were even all sorts of news articles showing, gold people reaching out and linking to other gold people and building all sorts of architectures. Now, to be fair to Sharon, it is true that I would have never predicted that it would have gone as far as you're going to see today, because the structures we're making now are incredibly sophisticated. Now, we knew DNA was doing the work back then because these types of architectures would assemble and disassemble based upon complementarity and temperature, right? If we went above the melting temperature of the DNA will unravel and the particles would disperse into solution. Whoops, why is this not working? I think this might be dead. Old-fashioned way. Oh, hold on. That's not working. Okay, so today we can now, does this need new batteries? Yeah. We can take, as you've heard, two particles that are the same size and designed to be complementary, and 100% of the time they will assemble into a rhombic dodecahedron. Rob beautifully talked about this and showed how that was the case. And to me, this is incredible, because now the DNA is placing every particle where it should be, making these highly faceted architectures. And so you might ask, what do we know now that we didn't know then? Well, we were getting stuck in kinetic traps, right? We were using longer oligonucleotide lengths, and the bonds were actually too strong. And so we were stopping en route to crystallization. And so the trick was to build architectures that maintain directionality, Just tagging things with DNA doesn't work here. Density is really important. Having oligonucleotides all the way around the structure, forcing the oligonucleotides to stand upright and adopt the directionality imposed by the rigid particle core is actually quite critical in building these types of programmable atom equivalents. But you'll see we have anchor strands, we have linker strands. The length allows you to control bond length. Every base you add, 2.6 angstroms of distance in terms of bond length. We've mapped that out beautifully. It's a very linear relationship. And then we have a recognition element at the end, which is a lot shorter than most people would design if you wanted to create duplexes, because you have cooperative interactions, many of these coming together at the interface between two particles that cooperatively bind and lead to a stronger interaction. If they're too long, you get stuck in kinetic traps. If they're short, 4 to 6 bases, they're strong enough to hold the structure together, but weak enough to allow the system to equilibrate and find the thermodynamic minimum. Now, this kind of gives you a clue in terms of how you can begin to think about deliberately programming the formation of different types of architectures. Because there are some similarities between atoms here, but there are big differences. And the really neat thing about this is you can define the properties of the atom independent of the bond, the size, composition, shape of the particle, or atom in this case, and the sequence length and density of the oligonucleotides. That's an unusual characteristic. With conventional chemistry, if I pick an element, I'm stuck with the type of bonding it can engage in. Here, the recognition element, the oligonucleotide, is independent of the particle size, or independent of the particle composition, right? So it actually depends upon particle size and shape, as you're going to see. And so now you can begin to deliberately think about building different types of architectures. And Rob introduced this idea of the complementary contact model. That's just a fancy way of saying that if I have a set of particles, particles will interact with one another to maximize contacts that will lead to hybridization, that will lead to bond formation. It's a bonding argument. It's not rigorously true, but it turns out it works over a large amount, greater than 90% of the design space that at least that we've explored to date. So if you want to make an FCC structure, you make self-complementary particles. That's easy with DNA, GC. If you want a BCC or cesium chloride type lattice, which you've heard about already, you have two particles of the same size that are complementary. And if you want to begin to make more exotic structures, you begin to play with the size ratios, which you can modulate based upon the choice of particles, the cores themselves, and the length of the oligonucleotides. And that's the other thing. You can change effectively the size of the programmable atom using those two parameters. And so if you think about this in terms of conventional chemistry, I teach a lot of general chemistry. This reminds me a lot of the way we teach chemistry with respect to things like Lewis dot structures and the octet rule, for example. The octet rule is about maximizing electron pairing. The complementary contact model is about maximizing hybridization, right? So you can, in fact, I teach this in general chemistry. You can begin to teach these types of principles to starting chemists, and they can begin to predict architecture ahead of time based upon some of these principles. We don't have the normal periodic table, but we do have a table of elements. And the beauty of this is it is not limited to the 103 elements. It is actually almost infinite in terms of complexity, defined by the composition, size, and shapes of the cores, and the types of oligonucleotides that you ultimately put on the particles of interest. And these are just some of the different types of materials that we've been exploring. That's why I asked the question about protein. I think proteins are the ultimate. I'm not going to talk about them here, but you can make them in a molecularly well-defined way, and you can begin to define where different types of recognition elements are on the surfaces, and you can actually control protein crystallization in a remarkable way using that type of principle in many of the design rules that we've established here, so that you can deliberately make structures that just wouldn't be possible if you didn't modify them with DNA. So where are we to date with this? We've now made and reported 90 different, this is not just our work, but also work people that have kind of built on this as well. Oleg's actually done quite a lot of great work in this area as well. 90 different unique lattices. We have over 100, because we have at least 15 that we haven't published upon yet, because we're in the final stages of developing them. And this has really expanded, being able to force interactions that ordinarily wouldn't occur, being able to realize lattices that we find in nature, mineral equivalents, for example, but also being able to make structures that have no mineral equivalent, that we don't find in nature. And so I think that's also fundamentally interesting and potentially quite useful as well. So what can't we do, or what would we like to be able to do? So recent challenges for colloidal crystal engineering DNA involve quasi-crystals. I used to get that question all the time, you know, can you make quasi-crystals? I would say, well, I don't know how to do that, but it turns out we do now. Stimuli responsive crystals, I'll talk a little bit about that. And then porous crystals. We've been asking the question, how do you begin to open up the porous material space along a length scale that's very difficult to access with conventional materials by using hollow types of particle building blocks and these types of programmable interactions to realize those architectures. And then non-centric symmetric lattices, which could have very interesting physical properties that I'll touch upon as well if we have time. Okay, so many of the structures that you see, we've embedded them in silicon so that we can actually silicon oxide, so that we can make electron microscopy measurements on them. And we didn't like that because that puts them into the solid state, and in certain cases we'd like to actually utilize them in solution as well. There are a lot of advantages to being able to go to the solid state, which we do take advantage of in the case of the silica type of treatment. But we came along with another type of process where we could begin to use coordination chemistry. I was trained as a coordination chemist from the start. And so I love this because you could, certain bases will interact with a silver ion and form a very strong coordination complex. And that can allow you to take a structure that is pretty fragile, right? When you take and program the formation of a colloidal crystal in solution with DNA, you get in a structure that's basically stable from room temperature up to, 80, 90 degrees, depending on how you design it. Here, if you modify with these types of silver links, silver ion links, you now can take them up to hundreds of degrees, and they still are stable in solution. You can begin to move them out of aqueous media into organic solvents as well. And so here's an example, and you have the ability to image them in their pristine state because you haven't modified them with a silica coating. And you can see these are again the rhombic dodecahedra, a BCC type of structure. You know that now because of all the things you heard from Rob and also what I've been kind of emphasizing today as well. But I want to point this out. This is not cherry picking. We're not going through and looking for this. This process is so good. If you look at the entire sample, it's nothing but rhombic dodecahedra. I mean, it's one of the most reliable forms of chemistry out there today. And so when I looked at these types of structures, I began to say, hey, we now have gone from polycrystalline architectures to single crystalline architectures. That means that we can begin to think about making devices that rely on the ability to make single crystals. And I'm going to talk a little bit about that as well. And we can also make, macroscopic amounts of these. In the early days, I used to say the world's supply would be like a femtomole of material. But now we're getting into the, I'm sure we can make grams. These are milligram type quantities of these types of structures. But you don't see loose particles. The particles effectively all go into the synthesis in this case. You can control crystal habit, and you do that in part by changing the DNA and changing the particle shape. The way we get valency control in this game is not through orbital hybridization, but through directionality imposed by particle shape. So cubes, for example, form cubic lattices. Octahedra will form rhombic dodecahedra. A rhombic dodecahedra will form octahedra. Okay, that's important again if you're thinking about utilizing these as devices and taking advantage of that macroscopic three-dimensional control as well. It doesn't stop there. You can see here other examples, the different asymmetries labeled there and the different crystal habits that you get. We can't dial in, obviously, crystal habit for any type of symmetry and go beyond the Wolf construction, but the point is we can get a lot of different types of crystal habits depending upon the types of structures that we ultimately generate by utilizing the right types of particle sizes, shapes, and oligonucleotides to get there. Okay, so from an electronic bonding standpoint, again, I think of VSEPR in terms of thinking about how different types of interactions ultimately take place. As I said, the way we control directionality and valency is in large part based upon particle size and shape. And so, you have triangular prisms. You'll end up forcing interactions in a linear type of fashion. They'll max the complementary contact model will tell you that these guys want to maximize interactions by building these stacks of plates. You're going to see that over and over and over again. If I have more three-dimensional types of building blocks, I'll get more three-dimensional types of networks. this is important because, you know, when you think about all the work that's done in the whole origami game and the conventional DNA nanotechnology game, the work that Ned Seaman really pioneered, and this type of work, what unifies them is if you want to build crystalline architectures, you need to be able to control valency. And the way they control valency is through crossover reactions that make a rigid building block that then drive subsequent bonding interactions. The way we control valency is by taking rigid building blocks, modifying them with DNA at high density, forcing the oligonucleotides to stand upright and to adopt the directionality imposed by that rigid. If you don't have that type of valency control, it's impossible to generate crystalline architectures, which is why I say it's a subtlety, but really important. This issue of being able to modify at high density the particle building blocks is critical to being able to realize many of the structures that I've been sharing with you today. But now you can force interactions, right? Small cubes, big cubes, concave cubes, convex cubes, cubes and disks. You know, how would you make this type of structure? Again, this issue of separating bonding characteristics from atom identity is really important because you can force interactions that ordinarily wouldn't occur. This is important, especially for the computational people in the room. Most people think about when we model things, what can we make by conventional types of techniques? This is turning everything upside down. The types of architectures we make here cannot be made in many cases by any other type of method. You know, even if you say, okay, let's kind of make something that's similar. And so there's kind of a feedback loop, and that's why I think it's so important for the computational people to be interfaced with these types of systems. Because it expands the playground of what's possible, and that'll be important with respect to some of the structures I'm going to share with you. We heard about tiling. I love the tiling talk yesterday. So we think about tiling too, because, you know, when you begin to take different types of shapes, you say, I can't put them together without generating architectures that have a lot of open space. Well, one way to circumvent that is to begin to play with shape complementarity. And so recently we've figured out how to take different types of shapes. We've gotten very good at making different particle shapes, primarily out of gold, but we can make them out of other materials as well. And so here you can see, you can, if you geometrically design these properly, you can modify cube octahedra with octahedra, and now you can fill all the space. And the trick here is to actually use short oligonucleotides. We actually had to design new ones, but that have, and this gets to your talk, a little shock absorber on them. Because to me, it's really remarkable that this works at all, right? Because one is you have to have the perfect match in terms of the shapes, right? And the sizes, the dimensions of the two particles. And it's impossible to do. You just can't do that from a synthetic standpoint. But if you use the oligo as a shock absorber, right, that can adjust for the slight differences in particle sizes here, you can get enough of a perfect match to force the formation of these, you know, really exotic types of architectures, the densely packed rectified cubic honeycomb shown here on the right. And then it's not limited to those. So here you can see octahedra and bitetrahedra, and you can see tetrahedra and octahedra. We can now begin to match these to form these really dense architectures where the oligonucleotide is really just a tiny glue that holds each of the architectures together and build these dense-filled systems. Quasi-crystals, the way we get there is to use structures with five-fold symmetry. So these decahedra, we've learned how to modify those types of architectures. I think Sharon, I believe she talked about this. These will self-organize into dodecagonal quasi-crystals. Sharon was critical in terms of assigning the structure of these. A lot of times when we get these, you know, we think we have a particular entity, but we have to go and do the simulations to actually assign the specific structure. That was certainly the case with this system. Talk a little bit about Vesper, right? And valency. One of the interesting concepts we've learned with Monaco Verde de la Cruz over the last few years is that if we reduce the particle size to a really tiny particle with just a few oligonucleotide links, they go from being programmable atom equivalents to electron equivalents. What do I mean by that? They will form a lattice with a bigger particle where many tiny particles will connect the bigger particles together into a particular lattice, but they remain mobile in the lattice. And a lot like in the electron C model for metals, they're roaming through that particular lattice and the glue holding the structure together. And that opens up this concept of metallicity. I think she talked about it probably last week when I wasn't here. But it also opens up this ability to design architectures that take advantage of that mobility. And so what we found is that in certain cases, you can take large particles with these tiny electron equivalents, and they will migrate through the lattice and then adopt areas of local concentration that effectively create a geometry that allows for a specific type of bonding, right? So you can kind of think about it as electrons occupying certain sites, and they're repelling one another to adopt a specific geometry that leads then to a connectivity that is more defined than the random movement throughout the entire lattice. And again, that's very similar, at least conceptually, in the way we think about things like Vesper, and that's allowed us to now realize a variety of other architectures, including the ones shown on this particular slide. Okay, what about properties? I think this is really important, and we're now at the stage where we should really be hammering on this. And I'll show you property number one that I think is really quite interesting, because I can't think of another material that has this type of property. One of the things we figured out very recently how to do is to make really large crystals. By large, I mean hundreds of microns, where we can actually see them easily in an electron or in an optical microscope, and see the faceted architectures and begin to inspect them in unique ways. And one of the things we discovered with the rhomic dodecahedra, for example, the BCC architecture, is that if we dehydrate these will just crumple like an accordion. Okay, and they'll go from a lattice parameter of tens of nanometers down to a single nanometer. And you lose, for the most part, almost all the order in the system. But if you rehydrate them, they go right back to the crystal. This isn't disassembling and reassembling. It's compressing, completely losing order, and then the number of particles in the box, so to speak, remain constant, and you resolvate. And this is where the DNA is not just acting as a glue to hold the particles together, but as a true blueprint to say, go back to that BCC architecture. And so, I say this is equivalent to, your home being knocked apart by a hurricane, and you come back the next day, and every board and every nail is in the exact place it was supposed to be. I mean, it's just a remarkable type of property that I can't think of being associated with almost any other form of matter. And the dimensions, the change in dimensions are enormous in this particular case. Now you might say, well, who cares? Why is that even ultimately useful or interesting? Well, it turns out there are big optical property changes that take place. These things are huge, very good broadband absorbers in their fully solvated state. Basically absorb all light put into them. But when you compress them, you then begin to open up areas of the spectrum where they don't absorb. They reflect actually quite well. And so how could you ultimately use that? For example, as pressure sensors. So mechanical type force sensors, because these things can withstand big perturbations and then expand right back into a pre-designed architecture on demand and the way you've actually programmed it to form using the right types of particles and oligonucleotides. What about other types of properties? So here you can see an example where we use different types of particles, different DNA to get, in the one case, a non-centrosymmetric lattice, and in the other case, a centrosymmetric lattice. And that immediately made us think of frequency doubling type properties. And so if you look to the right, that's exactly what we see. So this is a colloidal crystal now that has been designed to be a frequency doubler. And we can move that, presumably, all over the spectrum based upon the choice of materials that we ultimately use here. But this is the first example of this type of capability as well. Well, it's hard to say yet. I mean, I literally got that last week. I saw that in GroupMe, and I said, I'm going to show this at this talk. So I'm not going to get up there and tell you, where we stand with respect to the world record yet. But I will talk a little bit about this in the sense that when you think of porous architectures, this is an area that we haven't moved colloidal crystals into. But it's possible if we can make these open framework type which we can hollow out any sort of particle. We've developed a lot of the chemistry for doing that. We can modify with DNA, and now the complementary contact model will force these types of structures to align in a commensurate way to create these infinite channels, and that allows you then to begin to create lots of different types of architectures from the different types of shape complementary that I've been referring to. You build crystals now that have these open frameworks that then can be filled selectively filled with entities that fall in a kind of unique size space. This kind of fills in the gap between conventional zeolite type materials and metal organic frameworks, for example. And again, this is not a one-trick pony. If you look at this, you can make lots of different structures. These are related to 1D columns. These are from triangular prisms that have been hollowed out and then linked into the stacks that I shared with you earlier on. Under certain conditions, you can force these stacks then to assemble into more three-dimensional architecture, so the hexagonal systems here. The cubes are in purple here. What differs here is whether they're full cubes, truncated cubes, and whether they're fully hollow or only partially hollow. We have chemistry that allows you to control that. And then you can see the more exotic structures that come from things like octahedra as well. A lot of people in the whole metamaterial space talk about negative refractive indices. The holy grail. Can I create the Klingon? Was it the Klingon? The Klingon cloaking material. What was the Romulans? Okay. I wasn't that big of a Star Trek fan, but and this kind of really illustrates a point. I'm not an optical expert, so I don't want to put myself out there as one, but when we could make these structures, we went back to Corey and started saying, look, we now can make architectures that, again, I don't know how you'd make these in any other way. What optical properties should these exhibit, or could these exhibit, if we had the right building blocks assembled in the right type of way? And he came back to us and said, build one of these types of structures here from hollowed out octahedra. It's made of platinum and gold. It's got a platinum core and a gold shell. Hollowed out platinum core, you can see it in cartoon fashion assembled here, very similar to the architecture I showed you in the previous slide. This turns out to exhibit a negative refractive index, right? And he had actually told us to make it, gave us the right dimensions. We were able to go into the lab, make it, and then measure it. And that's that interplay that a lot of people have been talking about in terms of designing materials that have a particular property based upon this predictive capability and the ability to deliberately make architectures.
What determines that in certain transitions? What can you control here?
Yeah, he says we can. He said, with the dimensions and the choice of compositions, we're limited right now. So to say that we can do it is a different issue, but in principle, it can be done. Okay, so just if you look at this, I only took a few. I talked about shape memory and hyperelasticity, photonic band gaps we've been working on with Sharon, wavelength-dependent reflectors with George Schatz, and I mentioned the materials that exhibit negative refractive indices. If we think about where we're headed and what's really next, I think the important message of this presentation is that this is really quite a powerful way not just to understand what sorts of structures can be made, but to actually deliberately go out and target architectures. That's what we're ultimately after with this DNA approach, and I think we're there. There are parallels but notable differences between this field and conventional chemistry. I always use conventional chemistry as kind of a straw man to say, what can we do, what can't we do, where can we go beyond it? I kind of gave you a few examples of that. I think that's a good paradigm to kind of grow this particular area, and that's one that we utilize heavily at Northwestern. These new shape recognition type strategies, I think, are really expanding the phase space of structurally sophisticated colloidal crystal architectures. And that's going to really challenge, I think, the computational community to really think about what we can do with these types of materials that goes beyond what people have been thinking about with conventional metamaterials, especially those made by things like e-beam lithography. I think it's really important is elucidating structure-function relationships that translate into new properties, because we want to get into this ability to design properties based upon structural control. Make structures with properties that we want before we've even made those particular structures. And I talked about some of these, but also catalytic functions. We can begin to load up these host-guest type architectures with all sorts of interesting materials, catalytically active particles, viruses, for example, in the case of biological systems, enzymes in certain cases as well. Mechanical metamaterials, somebody talked about that. These framework architectures give us a great opportunity to begin to explore the mechanical properties of these types of systems. And then, in terms of challenge, I think what Rob's working on is really quite important. This, how do you begin to utilize a lot of these types of things? And DNA is great, but it's also very expensive and not amenable to making, kilogram quantities of it. Some of the materials that Rob talked about are. And so if you could get, I don't think you'll ever get to the point of this type of structural control of those, but if you can get far enough with certain ones, those might be incredible opportunities in terms of building functional materials that can be made in mass. And then this issue of being able to move from aqueous to organic media, I find that really interesting because I think it dramatically expands the scope of what you can do, because much of chemistry is in organic media and not in aqueous media. I will just stop there and acknowledge the folks that have done the work. These are some of the key people throughout. You can see Rob, he was a grad student in the group, 8 years ago, 9 years ago, and helped develop some of the early design rules that I shared with you. I'd be happy to answer any questions. Thanks.
Thank you very much.
Yeah, thank you very much. I have a question on your drying, hydrating shape memory system. So if you leave it dried for a long time, I guess these are thiol bond DNA molecules.
Yeah.
I mean, is it, and they're relatively close together, I suppose, in the gold, is it still not moving out of the contacts and fusing? So does it hold the structure for a long time?
So you're asking, do the particles fuse?
Yeah.
Yeah, so it's kind of interesting. So remember that when you put a shell of a oligonucleotide on a part, even at what I call high density,
yeah,
a large amount of the volume is water, right? They're highly solvated structures. There's electrostatic repulsion. So at really high density, there's still a tremendous amount of volume that's occupied by water. You get rid of the water, the oligonucleotides lay down on the surface, but they're long, right? And so they begin to take over that surface area and act as spacers between the particles. We don't see irreversible fusing with these types of systems. It's conceivable that you could, but we don't. Because you could say, well, maybe there's enough room that the particle come together. But I think the length of the oligonucleotide and just the sheer size and footprint of it protects the particles and acts as a spacer that keeps them from fusing together. Because if we add water, even after a long time, these things just snap right back into that rhombic dodecahedron shape.
Okay, thank you.
Yeah, Chad, beautiful talk. So I have one question here. When it comes to valency control, it seems in your systems, it's mostly about the generic shape of the nanoparticle. So have you thought about the strategy of having a patchy particle, for example?
Yeah, so it's shape and density. I keep emphasizing that the oligonucleotide density is really critical because that forces it to adopt the directionality imposed by the rigid particle core. Yeah, patchy, we've actually worked on going all the way back to the early 2000s. We recognized that early on. If you could take a spherical particle and put one type of DNA on this hemisphere and then another type on this, which we did, it's very painful. You have the equivalent of a linear type of directionality, right? And I can put X over here and I can put Y over here. Came to the conclusion that is a really, really difficult thing. Not worthy of pursuing, but a very difficult thing to do with the inorganic systems. And that's why I brought up earlier in the week this idea of proteins. I think of proteins as Mother Nature's nanoparticles. And with a lot of proteins, we not only know the size, the shape, there's an incredible diversity of shapes that I can choose, but we know the chemical topology, where the amines are, where the thiols are. And so I can take a really monodispersed sample of particles and I can modify with different types of oligonucleotides and control valency in a really grand style, and then force or program crystallization using many of the principles that we've talked about here. And that actually works. We have made a variety of different systems and actually published on them as well, where we take the belted proteins where we have one type of DNA here and another type of DNA in the surrounding belt, and therefore we can control lateral hybridization from vertical or vertical hybridization.
Okay, thanks.
Hey, Chad. Fantastic talk, as always. So I have a question similar to what Tobias was asking about, but at the other end of the DNA. So it's remarkable to me that you can collapse these things and get them to come back. I'm not terribly surprised by that, but what's remarkable is that you get the same shape back. The DNA bonds linking these things together, as we showed a decade ago, are transient. Do you have any sense as to whether or not it's sort of deforming, and then when it reconstitutes, it's the exact same bonds holding it together, or if the particles are reorganizing as you're rehydrating? It's
not the exact same, it's the equivalent. The positions end up the same. So what we got out of a lot of the work, early work with Monica in the simulations, I used to think of these, okay, we make this colloidal crystal, and we've got particle A here, particle B here, and particle C, and everything's fixed in space, and we've reached the thermodynamic minimum, and that's where it is. Well, not true. I mean, the particles sitting here, and the DNA is breaking and reforming, breaking and reforming. It's just you've got it in a spot where there are dozens to maybe upwards of 50 or 60 different connections to neighboring entities. So even though these guys break, it stays there. The chance of it moving to a different site is minimal, unless you perturb it like we did here. Now you perturb it and you get rid of the water and everything collapses, and now you've got that accordion effect. All the particles are in different positions now. It's not that every particle goes back to its original position, but it goes back to forming the rhombic dodecahedron, because they are all the same gold particle, they're effectively in the original position, or you've got a particle that was there that is the same in that particular spot again. The key is the DNA, even when you go to the accordion state, holds all the particles and keeps the fixed number of particles in that box the same. And that's why this works. So when you add water, everything starts moving and equilibrating, and it goes right back to that rhombic dodecahedron.
Yeah, so a follow-up question there is whether or not you're thinking about expanding on this sort of shape memory effect with the reconfigurability to actually perturb things out of the rhombic dodecahedron shape. So
No, this is just a model, because as you know, it's the tried and true, simplest system, two particles, same size, complementary DNA. 100% of the time, you're going to get a rhombic dodecahedron.
But the question would be, if you rehydrate it, if you're applying a stimulus that actually causes it to reform into something else, it seems like there's an opportunity there to use the programmability of DNA to actually drive it to a non-equilibrium type of shape.
Yeah, I agree. That goes to, where's our Berkeley friend here? He's gone. I mean, I was thinking the same thing when he was giving that talk. I think you could actually do that where you used a perturbation, or it could be a chemical perturbation, for example, that took a hairpin and opened it up, and now didn't change the building block, the size of the building block, but changed the recognition properties so that now a new structure is favored. So that you get out of the complementary phase favors rhombic dodecahedron to go to a different type of architecture. I think that's possible, and likely will be coming.
Okay, so I have a very general question. Of course, amazing talk, and we are here at the Kavli Institute for Theoretical Physics. So there is a bias for. No. It's a bias. I mean, there is obviously a push for theory and physics, yeah? So, and this is kind of where I come from. So the question is this. So looking at your talk, it seems like, I mean, probably it's not true. I'm sure it's not true, but in a way that the theory has progressed to the level that basically can keep up or even that. But the question is this. In your view, what would be the major theoretical, mostly conceptual part that you say, if you are able to advance it, we will be to move even faster?
As I said, and we made this a point in a couple of papers. One, a recent one in Science, maybe like 3 years ago, where we built these stacked architectures made of cubes, spheres, and disks. And they have this compressible property. They'll breathe, and different types of environments will change lattice parameter. They're architectures that no top-down lithographic method could ever make. They're architectures that no physicist, no chemist has even considered before. And to me, that's one of the most exciting things about this. This actually expands the playground, the toolkit that physicists should be looking at and considering in terms of defining new directions in terms of architectures that could lead to properties that we haven't found before. The example, you know, the closest we have to that right now are the open framework. We make the open framework architecture. I have no idea what we're going to do with these from a functional standpoint. I go to Corey and I say, who's a physicist, I say, go model these and tell me what architecture would exhibit a property that people ultimately care about. Well, he starts playing around with the negative refractive index, and he says, actually, it's weird. He goes, these things should support that. He goes, if you could make this particular architecture, these dimensions, and these gaps, it should exhibit that property. And so that's an example of that feedback. Nobody would have ever even considered making this type of, because there's no other way to make it. I mean, you couldn't use a conventional tool to make these types of systems. So I think the ability to program matter and structure control in the way I've talked about is a reverse challenge now to the physicists and all the modelers to say, okay, don't just think about your constraints of what's possible with, you know, conventional e-beam lithography and maybe the electrostatic crystallization. Now we can make these types of architectures. Can we begin to discover architectures through simulation that should exhibit properties that we want and go beyond what's possible with natural systems or even scientist-made systems in labs with conventional techniques?
Thank you.
Okay, any more questions? Okay, I think it's past 10:30, so let's move on to the coffee break. And for any more questions, we can continue. Thank you.